Welcome back to Discrete Math 2. Today we're going to look at derangements. And derangements are ways that we can redistribute something so that nothing is in the same place when we put it back. It's different from an arrangement because in an arrangement, things can go back in their order. I should mention before we start, if you go to TrevTutor.com under Discrete Math 2, there is a midterm covering everything up to this lecture. And I'll be doing a video on that as well, so if you need extra practice for all these topics, that is available. So derangements. Here's a question. Suppose we have 4 TAs dating 4 students. These students, of course, happen to be taking the class that the TAs are working in. How can we assign the TAs to mark tests, specifically these 4 students' tests, so that no TA marks their significant other's test? Because you know, if one of the TAs that are dating Sally happens to mark Sally's test, there could be some unfair marking there. So how many ways can we do this so that none of the TAs are going to mark their significant other's test? We're going to do this by brute force first, and I'm going to show you why this is a terrible, terrible idea. So we have 1, 2, 3, and 4, and these are going to be the TAs. Now what we want is we want the SO list so that we can't have a 1 there, we can't have a 2 there, we can't have a 3 there, and we can't have a 4 there. So what we'll do is we'll start the first one by placing a 2 where 1 is. And we'll just order the rest. So that's, okay, 2, 3, 4, 1. We don't see any of the numbers the same. Okay, so let's keep 2 here and let's see how many other combinations we can do. Well, instead of putting a 3 under the 2, we could put a 4 there. Actually, let's just put a 1 there. So we have a 3 and a 4 left. Well, the 3 can't go by the 3, so we have to put a 4 there. Then we have to put a 3 there. Okay, well, if we have a 2, we can definitely put the 4 under the 2. So we have a 1 and a 3 left. Well, the 3 can't go under the 3, so we put the 1 here, and then we put the 3 there. Okay, so these look to be all the possible arrangements of, or possible derangements of the first TA marking the second TA's significant other's test. And I don't really want to keep doing this because this is going to take a long time. So, instead, let's just use our good old Inclusion-Exclusion Principle. So let Ci be the condition that person I gets their significant other's test. So what we want is n of C1 bar, C2 bar, C3 bar, and C4 bar. Okay, so, well, if we have S0, of course we remember this is S0 minus S1 plus S2 minus S3 plus S4. Okay, well, S0, well, that's just 4 factorial arrangements, since it doesn't matter what order we give them out in. S1, we're going to choose one TA to get their significant other's test, and then the remaining 3 we'll just give an any random permutation. S2, we're just going to choose 2 TAs to get their significant other's tests, and then we'll order the rest however we want. S3, we're going to have 4 choose 3, and of course the last one is going to end up getting his significant other's test, but don't worry, that'll be uncounted when we do 4 choose 4 times 0 factorial for the last one. So if you've been following the inclusion-exclusion, you should understand this argument. If not, there's other videos that I've done, so you can check those out. Now, we just plug some stuff in. So this S0, this is going to be 24 minus 4 times 3 factorial, it's just 24, plus S2, it's going to be 6 times 2 is 12, minus S3, which is 4 times 1, plus 4, choose 4 times 0 factorial, which is 1. So this is actually going to be 9 possible ways And of course, if I did all the brute force method, I would have come out with 9 as well. So it's doable for 4 cases with inclusion-exclusion because, well, there's not that many conditions to do. But if I said find the way in a large classroom of 300 students to do this, you get pretty crazy because you'd have to have n of C1 bar, C2 bar, all the way up to C100 or C299 bar, C300 bar, and then that just gets to like S0 minus S1, all the way up to minus S299 plus S300, and that just gets ridiculous. So what we need is something better. So we're going to generalize it. We're going to use dn to be the number of derangements. I'm going to change this to a lowercase d because this is how I usually do it. The text I'm following uses an uppercase. I think it's ugly. Whatever. So we're going to generalize this to S0 minus S1 plus S2, so on and so forth. So the condition CI is always going to be I gets something back. We don't know what that something is, but they're going to get it back. So CI, if we have S0, then there's going to be n factorial ways to arrange everything, because we have n things we're dealing with. With S1, well, we're going to choose one of those n things to go back to its owner, and then we're going to organize the rest n minus 1 factorial ways. With S2, we choose 2 things to go back to their owners, and then we have n minus 2 factorial ways to arrange the rest. And of course this goes on until the very end, where we have n choose n, get theirs back, times 0 factorial. Okay, well, let's take a look at this. Let's expand this a little bit. We have n factorial minus, well, n choose 1 is just n factorial, no, sorry, this is n times n minus 1 factorial. I'm not going to bother expanding it, although I think I should. I'm going to expand this. N choose 1 is n factorial over 1 factorial n minus 1 factorial. Then we're going to add back n choose 2, which we know is going to be n factorial over 2 factorial n minus 2 factorial. And of course, this is still multiplied by n minus 2 factorial. And this goes all the way up to n choose n. So this is going to be n factorial over 0 factorial n factorial times 0 factorial. Okay, so we have this now, which is good because we can start doing some canceling. In fact, I'm just going to leave this last term out because I think it's really just equal to 1, so we'll just leave it as 1 there. Okay, so we have n factorial minus, okay, what cancels here? This cancels, this cancels. So we have n factorial over 1 factorial remaining. We add the next term where n minus 2 factorial, n minus 2 factorial cancels. So we're left with n factorial over 2 factorial. If we keep going, we're going to see this very nice pattern of just repeating this pattern. So we're going to have n factorial minus n factorial over 1 factorial plus n factorial over 2 factorial. So the denominator's going to keep going up by 1, and the signs are going to alternate. So this goes all the way up to the last one, which we see a 1 there. What happens when we take n factorial out of it? Well, let's just leave that as 1 right here, but really, we can rewrite 1 as n factorial over n factorial. So we'll leave it like that. Can we simplify this further? Well, of course we can. We can always make things a little bit simpler. let's just factor out an n factorial. Okay, so that's 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, all the way up to our final condition, which will be plus or minus 1 over n factorial. So this right here is the formula for the number of derangements. Very, very cool. In fact, what's even cooler is that this is very close to n factorial over e, where e is, of course, the exponent function, exponential function, or exponential constant, I should say. So that's 2.7128, something like that. Of course, you guys should all know e by now. So when we say d6, what we're really saying, actually, I'm going to use something that we can evaluate. So in the previous example, we did d4. So let's do d4 with this thing right here. So we have, let's see if I can get this in here. Of course I can't. Of course it's going to be difficult for me to do anything remotely simple. Okay. Again, I just want this in here. Okay, perfect. So d4 is going to be 4 factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial. Okay, so we can expand it in there, but this is really just 24 times 1 minus 1 plus 1/2 minus 1/6 plus 1/24, which, of course, we can simplify this a little bit nicer. So this is going to be 24 minus 24 plus 12 minus 4 plus 1, which is just equal to 9. So there you have it. Our formula here equals what we did with the inclusion-exclusion principle, which meets the exact same answer that the brute force method does. So at this point, we can pretty much claim that, yeah, this formula works. And in fact, if we just say d4 is roughly equal to 4 factorial over e, this is just 24 over 2.7, which, well, we know is just roughly 9. So this is a very good approximation, definitely. So if you're ever given a question, you could just write d4 is approximately equal to 4 factorial times e to the negative 1, or you could give an exact answer. If you're writing my midterm, I don't care, of course, because I'm not marking it, you're doing it yourself. But if I were teaching the course as a prof at a university, I also probably wouldn't care. So take that as you will. Let's do an example question. How many ways can 11 people enter a room and leave with a different hat? Okay, so people walk in, there's like a door or something, people just walk towards there, they're all wearing a hat, then they have this nice little hat rack, and then they put the hat on the hat rack, and then when they leave, they take a different hat. So there's a nice little hat rack here, and this is somebody else's hat. This person's like, I want that hat because it's not mine. And then he just leaves. Okay, well, this is the same thing as the number of derangements for 11 people, so D11. And this is just simply equal to 11 factorial. Well, this is roughly equal to 11 factorial times e to the negative 1. So that's our answer. I mean, there's really nothing more to it. What you could do instead is say, oh yeah, that's actually equal exactly to 11 factorial times the sum as I goes from 0 to 11 of 1 over I factorial. Sorry, this should be negative 1 to the I times I factorial. Or divided by I factorial. You could write that. You could put it in a calculator and solve it, but I mean, really, if you're being given a ridiculous number like 11 on a test, which is huge number for derangements, is probably good enough. Honestly, it's not that bad. So I know, easy question, very simple question. Here's something harder. In fact, it's so hard, I had to type the question out because there were so many words, and it wouldn't fit on screen if I wrote it. So, Ms. Petzolo teaches geometry and then biology to a class of 12 advanced students in a classroom that only has 12 desks. How many ways can she assign the students to the desks so that no student is seated in the same desk for both classes? Well, this is interesting because, well, first of all, it's saying how many ways can she assign, and then no student is seated in the same for both classes. So there's two parts to this. First of all, she assigns, and then she deranges. So, well, there's going to be 12 factorial ways to assign desks, right? Because, well, if you have a classroom, 12 people can go in the first, 11 in the second, 10 and so forth. And then derangement of 12 is just going to be D12. But, of course, we know D12 is actually 12 factorial times e to the negative 1, roughly. So we just multiply these two together, and then we get 12 factorial squared times e to the negative 1. In fact, when I say it's roughly, the best answer probably would actually be to say 12 factorial times d12. So not that bad, okay? But what if we say how many ways can she assign the students to the desks so that exactly 6 students occupy the same desk for both classes? Okay, this is a little bit more challenging because we assign, okay, so we assign, this is the same thing, but now we want 6 students to sit in the same desk. So we're going to choose 6 students to stay in the same desk. And what we're going to do is we're going to derange the remaining 6. So 6 students will not sit in the same desk from this derangement property here. So that's how you answer that question. So again, if I go over this example a little bit more, just to reiterate, first of all, we assign seats to the 12 individuals. Then we choose 6 of them to be in the exact spot for both classes. So for instance, if we have 12 desks here and 12 desks here, let's say we have some arrangement, so coincidentally, 1, 2, 3, 4, 5, 6, and they just happen to be in this order here. So we're just going to pick these 6 to stay in the same spot. Okay, so we assign them, and now we're keeping 6 in the same spot, and now we're just going to derange these ones. So these are all going to move to different locations. So this is your derangement. And that is derangement. That is the end of the first third of the wonderful course of Discrete Math 2. So I'm going to reiterate here. Of course, if you have any questions at all, leave them in the comments below. I'll answer them the best that I possibly can. If you go to TrevTutor.com and you check under Discrete Math 2, there is a midterm, and then there's one with solutions. Now, the one with solutions that's on there is going to be just a text document. I've just filled it out with answers. There's going to be a video coming soon. Probably if you're watching this now, you've already seen the video, or at least are aware that it's on the channel. And that's going to be a video guide that's pretty much the same as the text document. Some people don't like listening to explanations. Some people do, so I'm going to give you both options. So you can check that out. That covers counting, that covers the Catalan numbers, probability, and then of course all the inclusion-exclusion stuff. So you can check that out. And as always, any questions, leave them below. If this helped you, help your friends. Send it to them. Hopefully they'll get something out of this too. And I'll see you guys next time.